Hello, everyone. Welcome to the podcast. My name is Kishan, your host, and today we have a very special guest, Professor Dmitry Kireev. Professor Dmitry Kireev is currently working as an assistant professor at the Department of Biomedical Engineering at the University of Massachusetts, Amherst, USA. His research has contributed to the development of bioelectronic applications in healthcare and wearable technologies. Previously, he worked as a research associate at the University of Texas Austin. He completed his PhD work in 2017 at the Institute of Bioelectronics Research Center Jülich and RWTH Aachen University, Germany, working on graphene-based devices for neuronal and cardiac in vitro bioelectronics. He's a recipient of EMM Nano Scholarship and has performed his Master of Science studies in KU Leuven and Chalmers University of Technology in 2013 with majors in nanoelectronics. Dr. Kireev has published more than 40 research publications in leading scientific journals, contributing to the development of bioelectronics and 2D materials. When not working, he enjoys brewing his own beers. Dr. Kireev, welcome to the podcast. How are you doing today?
That's right. Thank you, Kishan, for introduction, and it really is my pleasure to be here. I do enjoy brewing beer when I'm not working, but starting with this new position, I haven't done it in a while, so hopefully soon. Yeah, but really glad to be here and to discuss the graphene and 2D materials and their bioelectronic applications.
Nice to hear. So recently you had been working on an interesting application of CVD-grown, which was on the topic of electronic tattoos. Could you tell us briefly about, what are electronic tattoos and what are some of the prominent end applications of these e-tattoos?
Sure. So to give a very broad intro to the field is, one would have to get back to 2010, 2012 for the first paper of John Rogers at Illinois at the time, currently Northwestern, when they developed this, they called it epidermal electronics. So they started with silicon or kind of normal electronics that they thin down, make it variable, flexible, stretchable, so you can put it on skin and use it for some sort of healthcare biosensing. Then back in 2017 at UT Austin, Professor Akinwande and Professor Nanchalu, they developed this technology of graphene tattoos. They kind of graphene-based epidermal sensors with kind of a twist to that being tattoos, because graphene is ultimately thin material. So once you make it, in a variable format, of course, there is some polymer to support it. But once you make it flexible and stretchable and you put it on skin, this is ultimately like a tattoo form that you can put on skin. The way you make it, I have them a little bit here with me. So these are literally graphene tattoos. I know I can get a little closer to the camera. So we make them on the tattoo paper. So like imagine in childhood, you have this tattoo, like you get a bubble gum maybe, and you get this tattoo that you put in water. You soak it in water, you put it on skin, and you kind of remove the paper and the image stays on. Exactly the same approach, but it's the graphene that stays on the skin that we can later use for healthcare biosensing.
Interesting. What type of graphene is used in these e-tattoos? And a follow-up question would be, and what is the role of graphene in these e-tattoos?
Right. So we are using CVD-grown one atom thick graphene. With that to say again, we're not using a single crystal graphene. It's one atom, single layer graphene. There are of course maybe multi layers here and there. There are of course multiple crystals. But we are using one atom thick graphene that's grown on copper in a CVD process. We don't grow it anymore ourselves. We just buy it. We use 6x6 inch, 15x15 centimeters pieces that we just spin coat PMMA. We etch the copper, and we just have this graphene with PMMA as a tattoo that we use for our processes. So So that's in terms of graphene and how we make it. On the role of graphene is really electrical conductivity. So at least for now, in all applications that we've done for now, it is just a matter that graphene is transparent, flexible, stretchable to some extent, skin conformable, but the important quality is electrical conductivity. Because all we do is, let's say we put it, one piece on the arm, and maybe we put it two on the forehead, and we just use this as electrical interface to the human body to measure electrical potentials. The simplest ones would be, as I mentioned already, if you put it on the head, you can measure brain activity or electroencephalogram, EEG. You can put it on the chest or maybe around your two hands. You can measure electrocardiograms to measure your heart activity. You can put it just on somewhere on your hands around the muscles, and you can measure muscle activity and decipher the muscular activity. Another project that has actually been done is we would put it around the eyes, on the top, bottom, left, and right of the eyes, and use it to measure electrooculogram. That's similar to EMG, but it's a slightly different application. When you look up, down, left and right, there is a certain repolarization and depolarization between cornea and retina happens. So there is some electrical potential that happens there that you can record with these graphene tattoos. And I was actually recorded and it was fed through to a drone, and the drone was flying depending where a person was looking, left, right, up, or down. So it really, to really shortly answer your question, is just electrical property, electrical conductivity. And then use case is really depending on where we place it and how we approach the electrical measurements.
Can you comment a bit about the specific advantages of CVD graphene in e-tattoos compared to, let's say, other type of materials that are also being used for these tattoos?
Right. Yes, you are right. I mean, there are also a lot of other. Right now, we can also talk about probably 20 different graphene types of things that people call graphene. There are flakes, there are laser-induced graphene, there are mixtures, there are composites. The really main advantage of CVD graphene here is that we end up with one atom thick, high quality, reproducible graphene layers that are also transparent, and atomically thin, right? If you use composites, you typically end up with thicker structures, maybe tens, 20s, sometimes hundreds of micrometers. Most probably, to really reach high conductivity in composites, you need to get multiple layers of graphene. That also results in thicker graphene, and also, multiple layer thicker results in it being non-transparent. But we want transparency. The term that we use for our graphene tattoos is imperceptibility, meaning it's imperceptible to you, to humans, to ourselves when we place it on our skin. Like, it's transparent, it's lightweight, you don't see it, you don't feel it, but it's there. So this is a unique set of advantages why CVD graphene is used there. That to say, you have to say, in advanced applications and latest applications of graphene tattoos, using one atom thick, a single CVD layer of graphene wasn't always enough for us because of the properties, because of the distribution of the properties. Often, if we make 100 of tattoos out of a single layer graphene, some of them would have amazing properties, but some would be orders of magnitude lower. And the reason for that, at least what we hypothesize, is a single crack or problem, or delamination, or maybe let's go with a defect in graphene, could cause really lower performance of the whole tattoo. So what we started doing is actually we would stack one layer of graphene with another monolayer of graphene to each other. We tried bilayer graphene instead of stacking two monolayers. It doesn't have the same effect. Stacking one monolayer on top of another monolayer has a superior effect than just using a bilayer graphene.
Can you talk a bit more about the influence of the thickness as well as the quality of the graphene and the impact it can have on the performance of these e-tattoos?
Well, yeah, so as I just started in terms of thickness, we did try kind of 1-layer, 2-layer, and 3-layer graphene. As the conductivity increases, with stacking 3-layer of graphene, that helps us. That helps in all the bioelectronic applications. But then, complexity increases as well, right? Because every time we need to wet etch, transfer, wet etch, and transfer. So there is some kind of a limitation that we had to choose in terms of how much of a properties do we want to increase to how much of the efforts can we spend. So using 2-layer graphene, kind of stacking one on top of another, has been helping us, and it is our working horse right now. The material that we're working with currently. In terms of quality of graphene, we've tried at some point, I want to say 3 different suppliers. We did see some dependency supplier to supplier, and dependency was much more visible with the monolayer graphene again. Like there is much more distribution in terms of properties of a monolayer graphene. But when we started stacking 2 or 3 layers together from different suppliers, the properties and the distribution wasn't significantly different. And as well, we haven't been using single crystal graphene. It's been always been polycrystalline, 10 to 20 microns crystals all over. So we'll see if we want to try single crystal graphene, if it helps or not. Yeah.
Besides the conductive properties of CVD graphene, are there other types of properties, such as, let's say, the piezoresistive properties of CVD graphene, that is also of interest for these applications?
I would say not. I honestly also have never seen too much piezoresistive properties of CVD graphene. I have seen some people, claiming and publishing that. In our application, especially when we put it on skin, right, and if we want to use it as electrical interface, we would actually want to avoid movement-related artifacts.
Mhm.
And usually when we create these wearable devices, even though graphene is stretchable by itself to some extent, we would still cut it in some serpentine shapes that would reduce all the motion or twisting or flexing dependent motion artifacts. So we actually want to avoid those passive signals that could come from movement. We only want to make sure that we're recording electrical properties purely and not movement related properties. That to say, yes, there are also there is a big subset of wearable electronics and wearable tattoos, let's say, where people would use some mixtures of graphene composites that would be piezoresistive or piezoelectric. That has there are different kind of devices. In our case, it's a purely electrical interface with the human body that we employ.
I see. And what functionality does single layer CVD graphene provide, for example, in comparison to graphene composites?
Well, it really is the conductivity. So just purely 2 kinds of the conductivity, right? The in-plane conductivity, that it's conductive, highly conductive in-plane. But then when we put it on skin, so when you transfer this tattoo on skin, again, just have to just get a little bit more technical numbers there. Graphene itself is supported by something like 200 nanometers of PMMA, because graphene by itself would not be self-sustained. When you put it on skin, there is graphene facing down. And if you look at your skin, if you want to look at it right now, it's not flat, right? It has all these grooves and hills and kind of, it's not perfectly flat. When you put this graphene tattoo on, it conforms to this micro curvature of the skin. So it really forms this beautiful, pure contact with the skin by itself, by self-adhesion, by kind of almost van der Waals adhesion. which is not happening with thicker materials. And because of this interface and electrical properties of graphene, you can now measure electrical signals that happening within the human body. At the same time, you can also inject. So you can actually use these graphene electrodes to inject current into the human body or heart, depending where you place it, depending what is your application. You can have bidirectional communication, not only sensing, but it can also stimulate the tissue.
So, as an application, I think you tested this for blood pressure monitoring use case.
Right.
Can you comment a bit about why did you pick that particular application? And I think there are a lot of work being done, for example, for cuffless indirect methods for blood pressure monitoring. So, what type of principles did you use there?
Sure. Yes, well, this is a big one. So cardiovascular applications overall is a big societal and healthcare need overall. And you just mentioned cuffless blood pressure monitoring systems. We want to go cuffless because the state of the art is a cuff, right? So those of you, I like to say that the ownership of this cuff sphygmomanometer, if you can pronounce it, is usually proportionally dependent on your age, right? So the older you are, the higher the chances that you probably have it at home. But it's this bulky thing that you put on your arm. It inflates, deflates, and it measures your blood pressure, systolic, diastolic, or mean arterial blood pressure. The problem with it is, well, first of all, it is 200 years old technology. It's been developed in 1700 something, so 200 to 300 years ago. The first concept was developed. The problem with it is, besides that you're just measuring a single value at a single time, there are a lot of there's a white coat syndrome. If you go to a doctor, your blood pressure probably goes up just by itself. So there's a lot of inconsistencies with a single set of measurement of blood pressure. That said, there's been a lot of efforts to develop these cuffless or wearable blood pressure monitoring systems. But what we did in our work, and this was a collaboration when I was at UT Austin, and it was a big collaboration with Texas A&M University. We used graphene tattoos that were placed over the wrist. Like there are two arrays of the tattoos that were placed over here. This is strategic location because this is where there are two major arteries. There's ulnar and radial artery that go through there. Now, we employed the concept of the so-called 4-point bioimpedance monitoring, 4-point bioimpedance. For those who are maybe more electrical engineers here, it is similar to Kelvin probe 4-point resistance measurement, which is, in contrast to when you do two probe impedance. So you could have two probe impedance. So you have two electrode, one here and one here. You can measure impedance. When you do this, you're mainly measuring the impedance of the interface. So whatever is happening on the interface, which is usually tens of kilo ohms of impedance of the magnitude. We want to measure impedance of the tissue. For that, we place 4 electrodes. You inject the current on the outer 2 electrodes, and you measure the change in voltage the inner 2 electrodes. By doing that, you're bypassing the interface impedance, and you're measuring the tissue impedance, which is few ohms in contrast to tens of kilo ohms over there. Now, by placing it over the artery, we're now starting to measure arterial impedance because that's where the current goes to artery because it's highly conductive salt solution. So then by measuring impedance of the artery slowly changes the volume with each heartbeat because the heart pumps the blood through your arteries. It slowly changes the volume, every time. That could be recorded electrically. So there's been a whole circuitry developed by our collaborators to do these measurements. And the bioimpedance, the change in bioimpedance that we record, is now correlated to blood pressure. Now I'm using the word correlated because it's not direct measurement. It is still measure of bioimpedance, but it's not exactly blood pressure. To correlate these two to blood pressure, we did measure control blood pressure. We had our subjects to go through exercise, so the blood pressure goes up and down. We had the control measurements, then we correlated using machine learning and correlation analysis. But after this correlation is done, we could forget about the control measurement and only use the graphene tattoos to measure blood pressure continuously, non-invasively, with kind of almost beat-to-beat variation every second sampling rate. Really important issue here is, perhaps Kishan, you already have that question, is you could do this with other electrodes, right? You could do this with a wearable wristband. Why do you need graphene tattoos? The answer to that is the need of doing this machine learning correlation. When you have a wristband, yes, you could do the same thing, by having a wristband and you kind of do the measurements. But the moment your wristband just shifts by 1 millimeter, 2 or 3 millimeters, your placement of electrodes, the way you measure, how you measure, when you measure, it all changes. So all this correlation that you've done for the past, I don't know, maybe an hour is just gone. The point that when you place these tattoos on exact same location, they remain on that exact location for the lifetime. That is the key factor of why graphene tattoos are essential for this application.
So in terms of analysis of, let's say, the feature that you collect, in your case, are you doing some form of a pulse wave analysis?
Well, yeah, so there's been a bulk of different correlation analysis, pulse wave velocity analysis, pulse transit time. There's been a bulk of there's been a lot of different features that we were able to record and then correlate to the change in blood pressure. Yes.
Can you discuss a little bit about the main features that you were looking for during the measurements?
The main features we just discussed, the pulse wave velocity, pulse transit time. So it's the velocity of propagation of how the pulse goes from one location to another. That's why we have not just single electrodes here, but we have two electrodes on each artery, so we could correlate how that goes from one to another. But then, as I mentioned, even when you're looking at the ideal trace of the blood pressure, it is complicated. It is subject specific. So this correlation that's been done by machine learning correlation has been subject specific, and that is perhaps one of the current limitations of this technology, which is universal for all kind of applications of the kind right now, is that it is subject specific. Unfortunately, we cannot just place it on a new person and use the previously built correlation. We have to go through some correlation before we say, okay, we're going to use these features instead of these features, because they just happen to work better on a different person.
Can you talk us through about the calibrations procedure that I suppose would be vital in such experiments, right? So what type of method or equipments did you use to assess?
Sure. Well, yeah, correlation, yes, this performing control correlation measurement, that has been done using medical grade, it's called FinaPress technology, that measures blood pressure. It has a cuff, so it measures blood pressure once, and then it has a finger cuff on the other hand of the subject. Sorry, the same hand actually. So it does measure blood pressure almost continuously, but it's somewhat invasive. It's not something you can go to sleep with. So yes, this correlation with control blood pressure is done, and that's how we see it right now. Like as a person, we need to get perhaps to clinic or to a doctor. You do this correlation once for the first an hour, and then you just go just using graphene tattoos, or ideally we want to have a universal correlation parameter somehow, something that you don't have to calibrate on each person, but perhaps you just have it there. You just have a built-in system, and you just put on these tattoos. You do a single set of measurements, and the analysis is there. But we are not there yet.
Would you consider, with reference to, for example, measurement acquisition in comparison to measurement data processing, where do you see the biggest set of challenges?
Well, the acquisition data systems and integrated circuits, being developed. There is no big challenge in that. The challenge is integration. Integrating the circuits with graphene tattoos somehow, that would be the challenge. Like, because right again, we're talking about these tattoos that come in the perfect contact with the skin, that remain there, but I need to read out from them somehow. You need interconnects. We do have interconnects, and we do have a way to record these signals in the lab, and it works well in the lab. Um, but it is slightly difficult to make sure that the same concept works in the wild, in somebody just do these measurements at home. Um, but in my opinion, that's an engineering challenge, and it is entirely solvable. I don't think that is an engineering challenge to solve for further translation if that happens.
In terms of production and stability of these electronic tattoos, how stable are these e-tattoos when they're exposed to ambient conditions over time? Are there any standard risks related to swelling of polymers, or their influence of temperature or humidity?
They are 100% stable. Like I've been using tattoos that been made 3, 4, 5 years ago. They remain well on the shelf. There is no problem on any stability. There are no challenges with that. There's not really a challenge. We're using just a layer of PMMA that doesn't swell. It's perfectly stable. Graphene itself is stable. There is no moisture or environmental instability over there. It is also entirely biocompatible for people who worry about biocompatibility. So there are no challenges associated with that whatsoever.
In terms of, let's say, the fabrication process, so the e-tattoo in this case consists of a thin PMMA layer and a patterned graphene structure. Is that correct?
Yes. Yeah.
And how do you manage to contact them? And because you also talked briefly about the impedance measurements, right? And how did you manage to contact such a structure?
Right. So yes, as I mentioned, we do have a technology that works in a lab, and that consists of the thinnest adhesive tape that we could find on the market. That is around 10 microns adhesive tape from a Taiwanese company. I don't remember it by heart. That we just evaporate gold on top. And on one side, we would solder it with this low temperature, room temperature soldering silver paste, to a wire. So it's we have a wire on the other hand, and on here we have this gold tape that we put graphene tattoo that partially overlaps the gold tape and partially contacts the skin. But we do need better solutions that we are currently working on. So there are a few unique concepts that we're trying to develop to have better, more reliable, maybe click and measure kind of solutions for the interconnects.
I see. In terms of biocompatibility of these electronic tattoos, what is the current situation on the biocompatibility related challenges and interfacing them directly on skin?
There are no challenges. So it is entirely biocompatible. As I mentioned, there is some misconception in the field about biocompatibility of graphene that's been fueled by some early works from tens of years ago, when people would use mixtures and composites of graphene and probably more, maybe closer to say graphite, getting this micrometer, maybe even nanometer scale of graphene particles that would be exposed to cells. And well, cells would be just obviously because of the size that they would get into the cells and cause some kind of cell toxicity. So that has raised some questions and concerns about graphene biocompatibility. But as mentioned already, there are dozens of different kinds of graphene. The graphene that we are using, CVD graphene, has been used to interface with cells. People would actually grow cells, neuronal cells on top of graphene, and it promotes neuronal growth. So it is actually entirely biocompatible in vivo. Here we're talking about something we just put on skin. There is no questions on skin irritation. We tested the status at UT Austin, here at UMass Amherst, I would say on over 20, 30, 40 people by now. Nobody ever complained about any irritation or any problems with biocompatibility. So there are none that is entirely safe and biocompatible.
With reference to the cell growth on graphene films, were these CVD graphene films bare or were they functionalized with certain molecules?
Well, there are different kinds of works. There's been a work where it was a bare graphene that was used for interfacing with cells as well. Normally, when you have this graphene microelectrode arrays or implantable graphene devices, it is a common practice to coat them with some proteins, which help cellular promotion. But there's been works where bare CVD graphene, even suspended CVD graphene, was used for interfacing with cells, and that was promoting and kind of advantageous for cell outgrowth as well.
How do you assess, for example, the functionalization of graphene with other molecules and their biocompatibility?
Well, that is a good question. Then it would not be a question of biocompatibility of graphene, right? Then it would be biocompatibility of whatever you functionalize graphene with. I don't think there has been many works on that, at least not on my radar, which perhaps is a good suggestion to to follow on this use. But typically, if people make biosensors, then the biorecognition elements that you put on graphene cannot be toxic, right? So if you're talking about sensing biomolecules that are normally present in human body, like antibodies or antigens, you won't be able to claim them as toxic materials.
So there are no, let's say, known or documented adverse reactions or side effects associated with graphene on skin reported so far.
Well, I would say yes, specifically for CVD graphene. If we can talk about, maybe different kinds of graphene, maybe composites of graphene that perhaps was made using certain chemicals that might have been toxic, and if they're not washed off properly, that might have caused some toxicity. But there is nothing to my knowledge of that could cause this problem.
And has CVD graphene biocompatibility compared specifically with, for example, other materials which are also used as skin interfaces?
Well, I don't think there's been. It's difficult to put numbers to this. There's always been works and kind of comparing one or another, two or three different materials, but there's been little works that would compare like a big variety of materials. And each time this bio cytocompatibility test is performed, there are always kind of different cells, different structures, different approach that was used. So it is slightly different to put number to it, to answer your question.
Are there any specific, let's say, key factors that can determine the success of CVD graphene integration with biological systems, for example, specifically on skin?
Right. Well, it's the electrical property, is the impedance that we measure. So impedance of the interface between the material and the skin. But I mean, yes, at the same time, there is adhesion, how well it adheres, optical properties, right? So you might want to think about aesthetics of these variables. Like if you need to measure from the forehead, for example, right? Perhaps you don't want these things to be visible, right? You might want to have these graphene tattoos that are transparent. I might have a few over here that you just can't see. But if I would have kind of different electronics that's maybe made of gold or something else, you would be able to see this. So this kind of optical and visual perception is I believe a big parameter of that. But electrical properties, electrical interface is main quantifiable metric.
Can you comment on the current regulatory status for interfacing graphene on skin applications?
That's a good question. I don't think there is any. I might be wrong, but I don't think there is none that I'm aware of.
Okay. So moving forward, what are you currently working on that keeps you still excited related to electronic tattoos?
There are a lot. I mean, there is still a lot of applications, right? So cardiovascular, as I mentioned, is one of those. We did do blood pressure monitoring before. What I want to move towards right now is more of a reason to cardiovascular diseases, right? So if you have high elevated blood pressure or lower blood pressure, wrong blood pressure, is already a consequence, right? And typically it's a consequence in 90% of the cases, according to WHO, the World Health Organization, it is a consequence of lifestyle, diet, and age. When we talk about cardiovascular diseases, a lot of cardiovascular diseases, such as hypertension, could be prevented by changing the diet and lifestyle. But the problem is that we don't know that there is a problem, right? I might not know that I have a higher or lower blood pressure until I go and check. And then if I go and check and I measure once, I don't know if there is a problem with me or not. So one of bigger predictor and something that develops earlier before you get to the problems with blood pressure, or heart rate, or coronary artery disease, for example, is arterial stiffness. So measuring arterial stiffness and the properties of arterial stiffness at different body locations on different people would mean a lot more predictor information to one's cardiovascular and overall health. Like I personally, dream of a system that, I kind of, again, ideally, it's not, I want to see these tattoos that you don't just put on and measure when you already have a problem, but something that, you can go to a local, supermarket or shop and buy them, put them on skin, measure, maybe somehow connect to your phone, and it's kind of you have this information locked down for years. We do need this long-term connected data that we could track over time, and then it would connect to my data when I will be logging in, and it will tell me, all right, Dmitry, your arterial stiffness is increasing over the last few months, and I see that you've been drinking a lot of beer at the same time. Accordingly to a data set of our 5 million people, or whatever number of people, if you continue like that for the next year, you have a, let's say, quote unquote, 70% chance of getting hypertension in 1 year. Something like that. So like getting towards a system that predicts and prevents cardiovascular problems before they happen. that's one of the directions that I want to work towards.
Perfect. So, on that note, Professor Kireev, it was a pleasure having you on the podcast. Thank you for joining.
Sure. Thank you, Kishan. It's been my pleasure being here.